I'll start my introduction today with tons of logos. My name is Raffael Schwanninger. I'm actually from the Institute of Power Electronics at Friedrich Alexander University. So not Fraunhofer, but that's okay. I get the confusion because the next logo is the Fraunhofer IASB logo, whom I'm working very closely with, especially the group of Bernd Wunder, who is the team leader of the DC-Microgrid group. And also the logo here, down here, is the Center of Analytics, Data and Applications, which funded part of the research that I'm showing you today. So, okay, the agenda today is basically three somewhat independent topics. The first is the DC microgrid itself and group controlled converters especially. Then we have offline impedance measurement and online impedance measurement, which again tie back to the DC microgrid, but can be seen as somewhat independent. So we'll start with the DC microgrid itself. That's the main reason why I'm working so closely with the Fraunhofer IASB. As you can see up here, they are building and they have their own DC microgrid. So DC microgrids are becoming more and more popular with, for example, factories, data centers, or EV charging parks. But the Fraunhofer IASB has their own DC microgrid. It's a plus minus 380 volt DC microgrid, which is connected to their own photovoltaic systems we can see up here. And lithium-ion batteries, hydrogen storage bidirectional, as well as DC charging office buildings. The lamp you can see up here is a DC lamp. And my desk that I'm working on today is also supplied by 24 volt DC. And the DC grid is also, of course, coupled to the AC mains via an active in-feed converter bidirectional. So for opportunities of impedance measurement, there are many opportunities to measure impedances in DC microgrids. One of them, for example, are those large storage systems, especially the batteries, where impedances can tell you something about the state of health, faults, temperature behaviors, and such. Also, the fuel cell, which the impedance can tell you things about if the membranes are too wet or too dry, as well with photovoltaic. But those impedance measurements go down to the millihertz range, so not really suited for the Bowden 100. So today what I will focus on is the DC microgrid itself, made up by, of course, the grid and all those converters linked to the grid. And what we will be looking at today is mostly stability, but there are also other possibilities to measure impedances in the grid, for example, for fault detection, arcing, or some connectors who aren't properly closed, as well as aging and such. So why do we need online impedance measurements? Well, let's assume we have this a grid like this connected to many different converters. So now we want to add another converter here. And we want to say, okay, we know this converter is stable, but will the whole grid be stable afterwards? And if it isn't stable, or if we say, okay, it's not stable enough, then what can we change to make it more stable? We can, for example, adjust control parameters, droop curves. We will see later what that is. And then we can make the grid more stable than before. So first, we need to talk a bit about how our DC microgrid is made of, and many others are also made of. So therefore, we will look at a very simple example. This example, we say, okay, we have our DC microgrid linked to the AC mains via an active in-feed converter. We have some load, which draws a current, and we have a photovoltaic. Now, the goal here should be to say, okay, we want as much power coming from the photovoltaic as possible, and the difference in power should either come from the AC grid or be directed back to the AC grid if the photovoltaic delivers more power than we, for example, need for this charging of the EV. So the first approach might be to say, okay, we just hook up both converters as voltage sources. So we have a voltage source here, that's the active in-feed converter, and we have a voltage source here, which should be a photovoltaic, and then we have some cabling resistance. Maybe this could be 20 meters of cable, and this is 40 meters of cable, and then we have our load, let's say 20 amps, and now we want to achieve optimal load sharing. So we say, okay, there's a certain current this photovoltaic can give, and the rest should be given by the active in-feed converter. As we can see, with such low resistances, load sharing isn't really possible. If we variate the voltage of the photovoltaic from 379 to 381 volt, we can see that this current change is a lot. So we go from over 40 amps down to minus 20 amps for the AIC. And if we assume we have a 12-bit ADC, we can see that, yeah, there's no real current sharing we can have. So a real possibility for load sharing is master-slave control. In this case, we have a master here, which supplies a voltage. So it's a voltage source and defines the voltage of the grid. And every other source is a current source. So in this case, we can set the current of the photovoltaic to a given amplitude, and then a lot less communication is required. A bit of a downside here is that we always need the master to be active, so we can't just turn the master off, or if there's a fault, the grid has to be shut down entirely, or we switch to another master. That's also possible, but we need a lot more communication, and also this master must be much more powerful than every other source in here, because it has to take all the current, if it needs be, of those current sources. A much more elegant solution, in my opinion, is group control. How does this work? So we can add, at first, we just add 1 ohm resistors to the cables here. In reality, that's not a really good solution because it would introduce losses, but we can just do it at first and then change this voltage of the photovoltaic down here. And as we can see, the change in current is now very slow if we just go from the 379 to 381 volt that we had before. And with our resolution, we can go a lot higher. Now we can have full load current sharing with the photovoltaic and the active in-feed converter. Now, how do we realize that in a real application? We don't want to put 1 ohm resistors in, but we use a virtual droop resistance. How do we get this virtual droop resistance into our converters? So the basic idea here is that we have a droop curve for our converter. So this would be the grid voltage. The nominal range should be 360 to 400 volts in this case. And in this range, we can change our current depending on the voltage. So this would basically be how we calculate the output voltage. We have the grid voltage minus some given offset voltage. In this case, for example, the blue curve, this would be 380 volt. And then we have a droop resistance. In the blue curve's example, this is 1 ohm. So we get the current here and maybe an offset current if we want to shift this droop curve up or down. This is especially necessary if we have regions with constant current. Usually we use those if the grid voltage, for example, is too low and our converter is current limited at some point. We can also have different droop curves. We can have some with a steeper slope and then be constant for a while, and then again a steeper slope, or steeper slope, less steep slope, and then a steeper slope again. As we like, we can have them bidirectional as the blue one or unidirectional as the yellow one. The droop resistance then is the the slope or the inverse of the negative slope here, as we can see them down here. For example, the blue curve has a constant troop resistance of 1 ohm, the yellow curve of 2 ohm, and in those ranges here, they are basically infinite. We will also see nonlinear droop curves in our system. Those can be put in willingly. For example, we can have this S-shaped droop curve if we like. They can have some benefits with stability, for example, but we will also see constant power sources. This is the blue one from 360 to 400 volt here. It's a constant power source. So constant power sources are given, the current is given by this, so our droop resistance isn't constant over the range, but dependent on the actual grid voltage. And as we can see, typically those constant power sources have a relatively high droop resistance. We can also have a constant power load. This is this orange curve here, and the constant power load also has a relatively large and non-constant droop resistance, and it's also negative if we use this model here. So when we go into small signal modeling, we can say, okay, our converter is now basically current controlled, where the current input is given by the grid voltage. So we can separate our converter's impedance from the output capacitance here, and then first calculate our converter impedance. This can be relatively complicated if we like. This would be a block diagram of a simplified block diagram of the current controller of a droop control converter. We have here our measurement input filter, our droop resistance, which can also be dependent on the grid voltage itself. We have a simple PI controller and a buck converter in CCM back here. We neglected here the delays, basically what we have seen in the last presentation to simplify it. But as we can see, this looks like a pretty complicated structure to model as an impedance, but in reality, it's often the case that it behaves like a low pass of first order, this converter here, as an RC basically, so we can model it as an R, L, and C. So the L part of the RLC is given by the corner frequency of our converter, basically, of the current control and the droop resistance, and then we can calculate a quality factor for our converter. As we can see, a increase in droop resistance doesn't only change the magnitude at DC, basically, but it also changes how this magnitude behaves over frequency. And we can also see that it has an effect on the phase. Here, the yellow curve would be aperiodically damped, so a quality factor of 0.5. And if we go down with the droop resistance, we can see that there's less and less damping, higher and higher quality factors, so that we can see a more pronounced resonance here. Still, the maximum impedance is lower than the impedance at a higher droop resistance. We can also see that with an increase in quality, so a decrease in droop resistance, we see a sharper phase change, and we can see that our converter behaves more and more inductive up to a certain frequency range. So after we've seen that we can find impedances for our converters, we need something to do with that, because just measuring impedances doesn't really help. So luckily, there are a few stability criteria here that we can use to identify a stable or unstable system. There are actually tons of them. One of them is the passivity criterion that I will talk about first, because it's very simple to understand. There are also lots of different minor loop gain criteria. For example, the Middlebrook criterion, which we have heard about today. In case of filter design, this is a bit too tough for DC grids or multiple DC converters. What we will look about today is the gain margin, phase margin criterion, but there are also many others. What's important to note here is that all those criteria are just sufficient criteria. So if you don't meet, for example, the Middlebrook criterion, but you meet the gain margin, phase margin criteria, your system is still stable. And of course, if you don't meet any of those criteria, your system can still be stable, but it's good to have a criterion to say, okay, now we have designed a stable system. Now we go back to our initial question, is this point stable here? So what we can do first is, okay, we can apply the passivity criterion, which says, okay, we want our converter or our grid to be passive. This means that it has no right half plane poles, or that the phase is between minus 90 and 90 degrees. Basically, what it says is we don't want to have a negative resistance in our grid. So every resonance we trigger should be damped and not magnified by our grid. So this is pretty simple. We can just measure the impedance at that point, apply the passivity criterion. In this case, it is met, and we can say, okay, our system is stable. Now, another way we can look at it is the minor loop gain criterion. We take an initially stable grid. So we can prove stability, for example, if we have only one converter and design it stable. And then we add, for example, the first load, this Z2 here. Then we measure both impedances in both directions, the load impedance and the source impedance. And then we apply one of those minor loop gain criteria, for example, the gain margin, phase margin criterion, which I will talk about in a minute. And then we can repeat that for every new load, because then we can say, okay, if those two form a stable system, we can measure here and measure the next load, and they will also form a stable system if they again work within this minor loop gain criterion. What's important to note here is that, of course, if I measure here, those two impedances here are put in parallel. So the impedance changes after each measurement. So how does this gain margin, phase margin criterion really work? So as we said, basically this source and load impedance are paralleled. So our total grid impedance looks a bit like this. We have this source impedance in the numerator. We said this is a stable impedance. And then in the denominator, we have 1 plus the source impedance divided by the load impedance. So if we assume the source impedance is stable, we can say, okay, this term must not destabilize it. For example, if this right term here is -1, this grid impedance would go to infinite. And also if it's less than -1 and only real part, then we can say, okay, now this grid impedance becomes negative. So it flips phase from, for example, 0 degrees to -180 degrees, and then it becomes active and probably unstable. So in this case, we apply a gain margin and the phase margin. In this Nyquist plot, for example, the yellow curve is our source impedance divided by the load impedance. This is the unit cycle, and then our phase margin opens up this range. This is the forbidden range. Here on the right, everything is allowed. And our phase margin opens up this angle here, and our gain margin increases the distance basically from 0 to the unit cycle of where we allow impedances. And in this case, for example, we violate the gain margin, phase margin criteria in this range. Usually such Nyquist plots aren't really the favorite of most engineers and designers. So we can look at it in a typical Bowden plot. So we can measure, for example, the source impedance in blue and the load impedance in this purple. And then we apply a gain margin, for example, 6 dB. So we raise the source impedance by 6 dB and say, okay, as long as the source impedance is lower than the load impedance, everything is fine. And then if there is a crossover point at which the source impedance becomes higher, the source impedance plus, of course, our gain margin becomes higher than our load impedance, we take a look at the phase here and say, okay, we define an allowed phase band around our source impedance phase. This would be those black dotted lines. The red one would be 180 degrees, so that's basically having no phase margin. And then we can see, okay, is the phase of our load within the region of our load phase? In this case, we can see here, okay, it isn't in the allowed phase range. This is the same as for the Nyquist plot, where we had the source impedance divided by load impedance in the not allowed range. This is this part here. So, okay, after we've seen that we can make statements about stability, basically, based on our impedance measurements, I will show you a bit our Bowden 100 test bench, how we use to measure our converters' impedances, and then show you a couple of different impedance measurements and how we can use them to determine stability of a system made of 2 converters. More converters would be even more complicated, so we will focus on only 2 converters today. So this is our Bowden 100 test bench. We have, of course, the Bowden 100 on the top here. It generates a test signal, maximum 13 dBm, so 1 volt, which isn't really a lot. Our converter probably wouldn't even notice that. We also use a wideband amplifier, which amplifies the 1 volt by 13 dB. It's not the power amplified by 13 dB because our output resistance of this amplifier is only 0.2 ohm, while the Bowden 100 output resistance is 100 ohm. This has 2 effects. One is that the maximum power we can then get from those 13 dBm is not, which is basically 20 watt, 20 milliwatt. We can go up to 100 watt with this amplifier. And of course, we also have a coupling transformer. And the inductance of the coupling transformer and the output resistance form a high pass. And the lower this output resistance is, the lower we can get the corner frequency of that high pass. Yes, so we also have those coupling transformers here. There are actually 2 coupling transformers in there. One is a 25 amp coupling transformer, which can go down to about 10 hertz. Most of the measurements I've made for this presentations are made with, or all actually are made with this transformer. We also have one for higher currents up to 50 amp, but with a lower inductance. So we can only properly measure above 100 hertz. This coupling transformer also has included isolated measurements, so we can measure our currents and voltages are measured internally and then fed back to the Bowden 100. We can also calibrate it, so we can get good measurements. So for our first measurement, we can look at a simple buck converter and not turn it on. So these are its passive components that we can see in the impedance. It's the output capacitance, which has around 260 microfarad. Its equivalent series resistance, which is about 20 milliohm. And we can see some parasitic inductance, which is also partially due to the leads that lead from the converter to the coupling transformer. And we can see that the phase starts at roughly 90 degrees. We can see here it drops a bit. That's because of the accuracy range of the coupling transformer here. And then we go up to 90 degrees again. Now we turn the converter on and give it some droop resistance. So we can get this graph here. Firstly, we can see that our RLC assumption isn't that bad. We didn't include the inductance, the output inductance here, but especially for the lower parts, it matches up pretty well. The green curve here with 250 milliohms, we can see the resonance because of the high quality. And for lower resistances, we can see aperiodically damped systems. What's important to note here is that this works because of the converter design. If we have a much less stable converter or a much lower output capacitance, we can also have them violating passivity criteria, for example. But in this case, we can see this is all fine. The other converter we usually have on the other side is a constant power load. So constant power load, as we have seen before, has a negative droop resistance, which is also pretty high in this case. So we can't even see the phase going down to minus 180 degrees. But we can see that it obviously violates our passivity criterion at low frequencies. An interesting fact to mention here, if we want to model it as an RLC, we don't only need a negative droop resistance, but also a negative inductance. Otherwise, this would not be stable, and then we get the phase curve here. So as we've seen with master-slave control, we can also have constant current sources. So a constant current source would have an infinite droop resistance. And as we can see here on the curve, the constant current source behaves mostly like the turned off converter. So only the output capacitance plus ESR plus the parasitic inductance. And we can also see that our constant current source can't really stabilize constant power load. This is pretty obvious if you look at it with a simple thought experiment. If we had them at a stable point and then we would increase the grid voltage by a bit, then the constant power load would draw a bit lower current, which would then lead to the constant current source even more increasing the grid voltage. So it would be unstable. The same if we decrease a bit the grid voltage, then our constant power load would draw even more current, therefore decreasing the grid voltage even more. But of course, on the master-slave control, we also had a constant voltage source in there. So this would be the constant voltage source here. If we also apply our minor loop gain criterion here, we have still included our 4 ohm droop resistance and our 250 milliohm droop resistance. We can qualitatively compare those to the constant voltage source. And as we can see, while even a low droop resistance can easily stabilize our grid, and it doesn't really help to increase the reduce the droop resistance, because while the cutover point shifts to the right, our phase also increases. The same goes for the constant voltage source, which has a cutover point here in the between, but because the phase comes from plus 90 degrees, it's basically the equivalent circuit would be just a output capacitance, a voltage source, and a inductance, because obviously we don't have a droop resistance now. We can see that a constant voltage source can have more problems at lower frequencies, but then the impedance also drops drastically So everything basically is fine. But if we have multiple converters in our system, it's usually preferable to have multiple group control converters, because each of them can help stabilize the grid. While if we only have one voltage source converter and a lot of current source converters, only the voltage source converter can really help stabilize our grid. So after I've talked about our Bowden 100 test bench, and it's very great, we use it in the lab very often if we have converters to design, or if someone sends us a converter and wants to know if it's stable or not. We often measure the output impedance with that. But if we want to have an online measurement, it's not really practical, because the coupling transformer is relatively large, which increases even more in size if we want to increase the current. And also adding a large inductance somewhere into the grid can actually destabilize it or induce additional resonant frequencies, which we don't want. So we came up with a measurement system that's minimally invasive if it's not turned on. So it should not have any high passive components in them. And we want something that's very small and compact, so that we can integrate it in our grid much more easily. So this is basically what we came up with. It's online measurement with pseudo-random binary sequences. The test circuit is very simple. We basically have a MOSFET here, which is turned on and turned off by this pseudo-random binary sequence. And this switches a larger resistor, which then draws a current. We can measure the grid voltage at this point, and then measure currents into two directions. So if we measure in this direction, we measure the impedance here. If we measure in this direction, we measure the impedance here. And if we measure the current down here, we can measure the total grid impedance, because it's the sum of both currents. So how does this pseudo-random binary sequence work? Well, basically, it's a sequence with very low autocorrelation, or the autocorrelation has a sharp peak at 0, which then induces a very broadband signal. The bit stream basically has a length of L, and the bit duration. The bit duration is the inverse of the switching frequency of this MOSFET here. So as you can see, we can go pretty high up here. And then the incoupled signal, the minimal frequency for the incoupled signal would be 1 over this bit duration times the length. And the maximum frequency is, depending on who you ask, 1/3 to 1/2 of the switching frequency of the MOSFET here. So if we switch with, let's say, 100 kilohertz, we can measure up to around 50 kilohertz. It's of course not really white noise, but it's noise with basically single frequencies selected out, and they go up from the lowest frequency in a delta of this lowest frequency. So if the lowest frequency is 10 hertz, the second frequency would be 20, then 30, then 40, and so forth. So this is then how it looked like. This is our measurement box with an integrated resistor, and here measurement cables and such. And this is how the measurement then looks like. It's a comparison of the Bowden 100, a simulation we made, and the injection with those pseudo-random binary signals. First, we can see that the Bowden 100 plus in-coupling transformer works very well. We match this simulation quite perfectly. We can also see that our pseudo-random injection isn't as accurate, but still pretty good. Up to, of course, half the switching frequency, where our phase deteriorates and the magnitude doesn't really matter anymore. So, okay. Uh-oh. I think my presentation is breaking down. One moment. Okay. Luckily, I was prepared for this. Oh, it seems to work. 1 minute. So there seems to be a certain time I can use PowerPoint. It's roughly half an hour. So I'm very sorry, but I will go on from here. So once we have all this data from the online measurements, what do we do with them? So in my opinion, it's good enough to have data. I don't want to do any more with it because I'm only interested in the incoupling of this data. But people have told me that you can just generate data for nothing. So what we have came up with is advanced data analytics for our grid layout. So we have came up with a few use cases for artificial intelligence. This doesn't only include grid stability, but also things like fault detection, like I said, shorts or arcing. You don't really need impedance measurements that much for it, but it can help if you know the impedance of your grid. And then if we have those if we have all the data and our artificial intelligence set up, we can build an intelligent DC grid. So the intelligent DC grid then can, for example, help with diagnostics or service, predictive maintenance, and such, or we can use it to assist with network extensions. So one small part of this is the impedance measurement that we do with our online impedance measurement system. So what we have is we build a digital twin network, for example, as a SPICE model. And then we define some input parameters, for example, the droop curve or some corner frequencies of filters, digital filters, for example, control speed, etc. And then with the help of very complicated models, we can then find some regions where it's very stable. So we can say, okay, minute changes in some parameters, for example, the output capacitance doesn't really affect the grid too much. So we can help with aging grids, for example. Then we implement it into our converters, measure it again with our PRBS measurement, feed it back to our SPICE model, and see if the changes we made help with stability of the grid. So I think I'm still on time, despite the short break. So as a short summary, what we talked about today was, in general, the DC microgrid. We talked a bit about droop control and stability investigation with impedances. I talked about the Bowden 100 test bench, our pseudo-random binary signal, incoupling, and in the end a bit about data analytics and artificial intelligence. I want to mention that this isn't really my main focus, so if you're really interested in that, just send me a mail and I will forward it to the experts at Fraunhofer IASB.